Hello, welcome to Maths with EJD. In this video, still on the probability, we are talking about cumulative distribution function. So let's see what that is about. The cumulative distribution function, CDF for short, of a random variable x provides the probability that x will take a value less than or equal to a specific value x. So that talks about the idea of cumulative. So if x is 5, right, we're looking at the probability that that a random variable can have probability up to the probability that the value can take your function can take a value up to that point, like that. So the cumulative distribution function is actually a function. It is a function that describes the cumulative probability. Cumulative is when we talk about something being cumulative, it's like it's adding up. So the cumulative probability up to a point x, up to the point x. So the CDF is useful because it encapsulates all the information about the probability distribution of a random variable in a single function. So mathematically, the cumulative distribution function is defined as f of x equals probability of the random variable x being less than or equal to a particular value x, like we said. Okay, so where f of x is the cumulative probability up to and including x. Up to and including x. Then we have p of x, big X less than or equal to small x, which represents the probability that the random variable x takes a value less than or equal to x. Okay, so that's how we define the cumulative distribution function. Now let's see some quick properties of that. What are some properties of the cumulative distribution function? So properties of the cumulative distribution function. First of all, it is non-decreasing. It's accumulating like the name goes. So it's non-decreasing. And that simply means that the CDF is always non-decreasing. As x increases, f of x either stays the same or increases. Okay, so the key is that it's non-decreasing. Then we can talk about the range. What's the range of values for the cumulative distribution function? So the cumulative distribution function ranges from 0 to 1, just like what we know of probability. Since we are talking about probability, the cumulative distribution function ranges from 0 to 1. Okay, so as x approaches negative infinity, f of x approaches 0, and as x approaches positive infinity, f of x approaches 1, like that. Another property of CDF is that it is right continuous. So the cumulative distribution function is continuous from the right. It's continuous from the right, meaning there are no jumps. When approaching from values greater than x. So it is right continuous. Okay, so having stated the properties, can we now look at some examples of cumulative distribution function? The first example we'll be looking at will be discrete. For discrete random variable, we have the binomial distribution to represent that. Binomial distribution. So here, consider a discrete random variable x that follows a binomial distribution. With parameters. In case the idea of binomial distribution is not well known to you, you can check I think 2 videos before this. We talked about binomial distribution, discrete random variables. So we actually clarified everything about binomial distribution. So with parameters n equals 5, that's the number of trials. Okay, and p is 0.3. That's actually probability of success. In each trial. So the variable x represents the number of successes in 5 independent trials. Okay, so to solve this, right, we know that the probability mass function, the probability mass function. Of course, this is attached to discrete random variables. Talk about probability mass function, which is PMF. Probability mass function for a binomial random variable, is given by probability that x is equal to x is equal to n combination x, probability of success raised power x, that's p, then into 1 minus p raised power n minus x, that's probability of failure raised power n minus x. And here, our x is discrete, so we have 0, 1, 2, and so on and so forth up to a particular value n. So if this is the probability mass function, the cumulative distribution function f of x will actually be equal to probability that x is less than or equal to x. So you can see here that this is the probability that of a specific point x, right? But cumulative is talking about a probability of x less than or equal to x. That means you have a range of values up to a particular point x, right? So the CDF f of x equals p of x less than or equal to x is the sum of the probabilities up to x. For example, to find the probability that there are at most two successes. So at most two successes now. That's the focus. In that case, we're actually looking for f of 2, which is probability that x is less than or equal to 2. And if that is the case, we're dealing with a discrete case now. That means probability that x is equal to 0 plus probability that x is equal to 1 plus probability that x is actually equal to 2. So it's cumulative, right? So if you're looking for the probability that x is less than or equal to 2, then it means everything we can get up to x. That's what that represents. So if we now consider, so if we go back there now, so it means we need each of these probability of x, that x is 0, probability x is 1, probability x is 2. So from that expression, right, where we have probability that x is equal to 0 is simply going to be the number of trials, right? That's 5 combination 0, here our small x is 0. So we can say for probability that x is equal to 0, for instance, then that now, based on the formula, multiplied by the probability of success is 0.3 as we have. So we can list out all these things. N is equal to 2. N is equal to 5. We have 5 trials. We have the probability of getting a success based on whatever success we need is actually 0.3. P is 0.3. And I think that's about all we need. So we have 0.3 now raised to power x, which is 0, multiplied by, of course, if p is 0, then 1 minus p is equal to 1 minus 0.3, and that is 0.7. I get, yeah, 0.7, like that. So we have 0.7 raised to power 5 minus 0, going by the formula. Okay, or I can make things neater. Let's make things neater. Let's not be that clumsy. Okay. Of course, if you have not subscribed to this channel, be sure to do that, because there's a whole lot to learn here. And also, if you also need to hit the notification bell so that anytime a new video is released, you can get alerted. And then don't forget to comment, like, and share so that more and more people can benefit from all this. Okay, so we know from the formula, we need n, x, and p. That's all we need. But we already know our values of x. Now, this is like when small x is 0, small x is 1, small x is 2. That's what all of that means. Okay. Then, so it means that number of trials, that's 5. Probability of success is 0.3. Automatically, 1 minus p would be probability of failure, which is 1 minus 0.3. That is 0.7. So with this in place, then we can get each of these things. So probability that x, okay, that's just to list out those points. So probability that x is equal to 0 is actually 5 combination 0, 0.3 raised to power 0, then 0.7 raised to power 5 minus 0. Okay, so that means you have 5 combination 0, 0.3. Okay, we can begin to break things down, right? Okay, let me just do 0.3 raised to power 0, then 0.7 raised to power 5. Okay, so that this is now 5 factorial over 0 factorial, 5 factorial, because that's just going to be 1. Then 0.3 raised to power 0 is actually 1. And all we have is, so we can say 7 over 10 raised to power 5. I think that's an easy way to handle that. So, of course, this is 1 times 1 times 7 raised to power 5 over 10 raised to power 5. That should be like 0.1681. So overall probability that x is equal to 0 is simply okay. Okay. That's okay. Let me use Desmos so we can be sure of what we are doing, right? Let me go Desmos to do these calculations. So okay, so this now, then I go to Desmos. Okay, graphing calculator. So we can do our calculations right there. So here now we need 0.7 raised to power 5. That's raised to power 5. And that is 0.16807. So that's simply 0.1681. That's probability that x is equal to 0. Okay. Then let's do for, okay, let me go back. Yeah. So now we need probability that x is equal to 1. That would be 5 combination 1. Then p, which is 0.3, is raised to power 1 now. Then 0.7 raised to power 4. Of course, that will be 5 combination 1 is 5 factorial all over 1 factorial 4 factorial times 0.3 times 0.7 raised to power 4. Okay, so this is 5 factorial all over, okay, this is 5 factorial itself, right? Can be written as 5 times 4 factorial all over 1 factorial. 1 factorial is 1, right? Times this 4 factorial down here, so this cancels out, times 0.3 times 0.7 raised to power 4. So that we have 5 times 0.3 times 0.7 raised to power 4. So we go back to Desmos and get the results. So 5 times 0.3 times 0.7 raised to power 4. So 0.7 raised to power 4. So we have 5 times 0.3 times 0.7 raised to power 4. So that is 0.2881, 0.2881. So 0.2881. All this is 0.2881. That is the probability that x is equal to 1. Then we also need probability that x is equal to 2. Did we do that right? That's 5 times 0.3 times 0.7 raised to power 4. So that is 0.2881. Okay, so I'll check that again before we continue in case there was an error. I think it's fine. Okay, so what about probability that x is equal to 2? probability that x is equal to 2 is simply 5 combination 2, 0.3 raised to power 2, then 0.7 raised to power 3. Yeah, that's how it goes. Yeah, that's how it goes. So we have 5 factorial all over 2 factorial times 0.3 raised to power 2 times 0.7 raised to power 3. So this is 5 factorial over, or better still, we can say 5 times 4 times 3 factorial all over 2 factorial. 2 factorial is simply 2 times 3 factorial. So this cancels out. So we have 0.3 squared times 0.7 cubed. So that's 2 here is 1, 2 here is 2. 5 times 2 is 10 times 0.3 squared times 0.7 raised to power 3. So we go back to decimals and do that. So 10 times 0.3 raised to power 2. Okay. I think something is wrong here. I was wondering, yeah, something is actually wrong here. This is actually 5 times 0.3. I was a bit I was really wondering. Okay, fine. 3602. 3602. So this is actually 3602. Yeah, so this is 3602. 0.3602. So then for this now we have 10 times 0.3 squared. 10 times 0.3 raised to power 2 times 0.7 raised to power 3, raised to power 3, yes. So that's 0.3087, 0.3087. So back to that, we have 0.3087. So that's the probability that x is actually 2. Well, and since we are talking cumulative now, we can say therefore, so we can say therefore, f of x, f of 2 is now probability that x is less than or equal to 2. And that is equal to all these values now. So that's 0.1681. Or, if you don't mind writing it all out, I think it's fine for emphasis. So that is probability that x is equal to 0 plus probability that x is equal to 1 plus probability that x is equal to 2. And that will be 0.1681 plus 0.3602 plus 0.3087. And that is equal to 0.8370. In that case now, this means there is 83.7% chance, 83.7% chance of obtaining two or fewer successes in 5 trials. Okay, so that's a cumulative distribution function for a discrete random variable, or a discrete for binomial distribution in particular. So let's take the second example where we talk about a continuous random variable as an example. For continuous random variable with specific focus on normal distribution. So we have this, or better still, this. Okay, so there's this perfectionistic trouble I always have. Okay, so I think what I did before is fine. Yep. So this right. for a continuous random variable, for a continuous random variable x, following a normal distribution with mean mu equals 0 and standard deviation sigma equals 1. For a continuous random, for a normal distribution, this is the mu is always 0 and the standard deviation is always 1. So that, of course, that is for the standard normal distribution. Normal distribution. So the CDF, the cumulative distribution function, does not have a closed form expression. A closed form expression. So, however, it is expressed as an integral of the probability density function. You know, integral is like summation in continuous random variable. Instead of the normal summation we do for discrete. So as an integral of the probability density function, PDF. So such that, you know, our f of x is actually the same thing as probability, that x is less than or equal to small x. So instead of having to sum up here, we sum from negative infinity to a given x. So 1 over square root of 2 pi, 1 over square root of 2 pi, e raised power minus t squared over 2 dt. So no closed form. So actually, to find, for example, f of 1.5, you know, this is not discrete now, which represents the probability that a standard normal distribution, that a standard normal distribution, that a standard normal random variable, rather, normal random variable is less than or equal to 1.5. So we have f of 1.5. So you can use the table, the normal distribution table, to get this, and that is approximately 0.9332. Okay, since it doesn't have a closed form, so we can use the table. So, and this tells us that there is a 93.32% chance that a randomly chosen value, from this normal distribution will be less than or equal to 1.5. So the CDF, of course, is useful in statistics such as finding confidence intervals or determining critical values in hypothesis testing. So that's one very good use for it. So yeah, I think I'm going to talk about some specific use cases afterwards. Okay, so let's take one more example. before I talk about some applications. So let's take another example, say 3 now, where we talk about, let's take another continuous random variable. Which is the exponential distribution. So for exponential distribution now, so consider a continuous random variable x that is exponentially distributed with a rate parameter lambda equals 2. So the exponential distribution the exponential distribution is often used to model the time until an event occurs. Such as the time between arrivals of customers in a queue. Customers in a queue. Okay. So the CDF, the cumulative distribution function of an exponential function, is given by f of x, which is equal to 1 minus e raised power minus lambda x, where x is always greater than or equal to 0. That's the CDF of an exponential distribution. So now to calculate the probability that x is less than or equal to 1, that's more like we're looking for f of 1. So that will be 1 minus e raised power minus 2 times 1. Okay. Lambda x, right? Lambda is 2, and here x is 1. So that simply means we have 1 minus e raised power minus 2, and that is approximately 0.8647. 0.8647. So this simply means that there is an 86.47% chance that the event will occur within 1 unit of time. So if the units of time you're using is minute or hour, so that will go for that. Okay. So now let's talk about uniform distribution. The other time I said last example, right? But uniform distribution is yet another example we can consider. So for uniform distribution, so the uniform distribution has its own unique way of its unique definition. So if X is uniformly distributed over the interval, A, comma B. This is actually a closed interval, meaning that both A and B are part of it. So it was an open interval, then it means that everything lies between A and B, not getting to A or B. So we say the CDF is a linear function, and that is f of x. In fact, is linear and step function too. So the value is f of x is 0 when x is less than a particular A. Then it is also x minus A over B minus A as x lies between A and B. That's A less than or equal to x less than or equal to B. And lastly, it's actually 1 when x is greater than B. So this is the definition of the cumulative distribution function of the uniformly distributed random variable of the uniform distribution. Okay, so for instance, if x is uniformly distributed between 2 and 5, uniformly distributed between 2 and 5, to find the probability that the random variable x is less than or equal to 4. Okay, so that means we have f4 to be equal to f4 is equal to 4 minus 2. So this function now, it's a step function. So when x is less than, for instance, if x was less than 4 now, then we can say that it's 0. But if x lies between a particular interval, I mean, if x is less than 2, if x is less than 2, then the function is 0. But because x lies between 2 and 5 now, so the probability that we get x less than or equal to 4 would simply be, so it means this is going to be applicable. This second part is going to be applicable. So we have x minus A over B minus A. So that's, so we have 4 minus 2 over 5 minus 2. Because A is 2, B is 5. Now we have x to be less than or equal to x, and that x is actually value 4. So in this case, we have 2 all over 3, and that is approximately 0.667. Okay. So there is a 66.7% chance that a random variable, or rather a random value from this uniform distribution, is less than or equal to 4. Like that. Okay, so those are 4 different examples right there. Let's quickly talk about some applications as we draw a curtain on this. So let's look at some real-life applications of CDF, of cumulative distribution function. So it was mentioned earlier that it is useful in statistics. So in statistics now, we can use it for finding confidence interval. Okay. Or determining critical values. Determining critical values in hypothesis testing. In hypothesis testing. Okay. Then other applications, we have in insurance, we can use CDF in insurance. So it helps to determine, to determine the probability of claims. You know, in insurance, right? Talk about claims. So the probability of claims reaching a certain level. So if you already know the probability that the claims by clients is going to reach a certain level, so you can prepare adequately for that. So you are not caught unawares. And it's of course useful in finance. So in finance, so it is used to model stock returns, to calculate the probability of returns being above or below a certain threshold. Okay. Then of course it's useful in engineering. It's useful in engineering. So since it's cumulative, right? So you want to know how things can add up to a point. So in reliability analysis, reliability analysis, the CDF, the cumulative distribution function, helps estimate the probability that a system or component will fall within a certain time frame, will fall within a certain time frame. All right, so with that, we come to the end of cumulative distribution function and how they are applicable. So, of course, we have seen that the CDF is a foundational concept in probability and statistics, and it provides essential information about the likelihood of different outcomes and helping to model and interpret random phenomena in various fields. So be sure to subscribe to this channel so you can get more of this. And of course, hit the notification bell so you can always get alerted when a new video is released. Then don't forget to comment, like, and share so that more and more people can benefit from the things you're learning here. See you.